I'm Kentoneta from NLJ. I will talk about the instrument, not observation or theories. We are developing a new post-processing method for high-contrast imaging. This method is called the coherent differential imaging on specular linearing, CDS-SAN. We propose to implement this method as a guest algorithm for Roman CGI to achieve higher contrast. I will briefly present experimental result of the CDS-SAN method. Direct detection of Earth-like exoplanets requires 10 to minus 10 contrast. Scatter stellar light, so-called speckles, caused by wavefront aberration can be suppressed by wavefront sensing and control system. However, deformation of the instrument causes the fluctuation of speckles. Fluctuating speckles limits the achievable contrast. Now we are developing a new post-processing method, which is called the CDS-SAN, to suppress the fluctuating speckles. This method requires only control software for a wavefront control device and a camera. We propose this method to the CGI CPP as a guest wavefront sensing and control algorithm. We are conducting laboratory demonstration at NLJ. Center image is integral image in speckle fluctuating situation before the CDS-SAN method. We calculate the mean contrast in the target region. Mean contrast before the CDS-SAN method was 3.4 times 10 to minus 8. Right image is after CDS-SAN method. The mean contrast in the target region was 1.6 times 10 to minus 8. Contrast improvement by the CDS-SAN method was 0.47. Now we are conducting demonstration to achieve better contrast improvement. I posted URL to access our poster on Slack. Please see our poster for more details. Thank you.
Reni, you should be able to share your screen.
Yes. Can you hear me?
Yes.
And can you see my screen?
Yes.
All right. So, hi everyone. This is to give you a brief overview of our current work on detecting population 3 stars through their tidal disruption signatures and their observational feasibility with JWST and Roman. Okay, so in short, population 3 stars are the first stars that were formed in our universe, and their primary compositions are hydrogen and helium. These POP3 stars are very massive and also very short-lived. Now, these POP3 stars are important to understand the complex nature of our present-day universe, mainly because they are the first factories to synthesize the heavy elements at their cores and afterwards distributing these metals to their surrounding IgM and ISM by supernova explosions. And from this metal-rich gas, next generation of population 2 and population 1 stars were formed. However, these POP3 stars are very difficult to detect mainly because of their short lifespan as well as their cosmological distance. And in this work, we have proposed a very unique method of detecting these POP3 stars by probing their tidal disruption events. Now, tidal disruption events are a very unique transient occurring when a star gets disrupted by the huge tidal force of massive black holes. And this produces a very luminous emission. And in our work, we have tried to model this TD emission of the POP3 stars at very distant galaxies and also their observed fluxes and their detectability with JWST and Roman. And here you can see the observed light curve of one example of this population 3 TDE, and we see that this light curve, this observed flux stays above the detection threshold of both JWST and Roman for a very long period, for a significant period of time. And we have also calculated the observed rate of such POP3 TDE. And the main factors that goes into these calculations are the survey sky coverage fraction and the survey duration. And due to the small field of view of JWST, we estimated that the detection rate with JWST will be very low. However, with the high sensitivity and large field of view of Roman, we might be able to detect quite significant number of such events. And we have calculated that this predicted number of such POP3 TDs will be 50 per year with high latitude wide area surveys. And this is the takeaway message. And I thank you all for listening. And please check out my poster I have uploaded in Slack channel, and do check out our paper on this. Thanks.
Yep. Okay. Oh, there we go. Wonderful. Hi, everyone. Oh. Okay. Hi, everyone. My name is Noah Downing. I'm an undergraduate at The Ohio State University, and I've been working together with the Roman Astroseismology Wide Field Science team to simulate astroseismic detections for the Roman Galactic Bulge Time Domain Survey. And then, that's it. Oh, there we go. Okay. So as we learned yesterday, astroseismology is the study of stellar oscillations, which cause fluctuations in a star's brightness that we can see through time series data. And we can probe these oscillations for stellar parameters such as a star's mass, age, or radius. And the Roman Galactic Bulge Time Domain Survey is uniquely situated to provide a wealth of time series data in the galactic bulge for oscillating red giants. And these red giants, more specifically the core helium burning phase of the red giant branch known as the red clump, are powerful stellar population, we can use as a powerful stellar population tool in the galactic bulge. And to simulate this, this astroseismology, I used real Kepler data and modified it to follow the nominal observing strategies for the Galactic Bulge Time Domain Survey. I also included two different noise models, one from Matthew Penny and then one from Robbie Wilson, which includes saturated star photometry, as well as modifying the cadence to see how we could improve our astroseismic detections. Oh, there we go. So I think this is neatly summarized in this figure here, which shows power spectra of a few different cases of stars. So the top row we have the lower red giant branch, the middle row we have faint red clump stars, and then the bottom row we have brighter red clump stars. And then each column is separated by either Robbie Wilson's or Matt Penny's noise model. Matt Penny's having a noise floor of 1 millimagnitude, whereas Robbie Wilson's provides variation for brighter stars. And then also between a 15-minute and 7.5-minute cadence. And the key takeaways from this are that we can notice that our astroseismic signals, these peaks in the power spectrum that we see, fall really close to the noise floor in the red clump. And we can improve these dramatically by implementing a faster cadence or doing more experiments on saturated star photometry to lower that noise floor we expect to see in the galactic bulge time domain survey. Thank you.
Hello, everyone. My name is Sachi Virasuri. I'm a postdoc at Carnegie Science. So, as we know, with Roman and other future surveys, we are going to be bombarded with lots of observations from emission line redshifts and galaxies. So we need to have models that can predict these observations and also to tackle these many observations. So how are we going to do that? If we look at the current state of simulations that we have, the zoom-in simulations are limited by statistics, and the cosmological volume simulations are limited by resolution. So one way of tackling that is using semiotic models, which can offer us both statistics and the resolution needed to overcome this problem. And the model that we are using is called Galacticus by Benson 2012. So we can generate merger trees of galaxies by applying and we can apply the galaxy physics by solving ODEs. So the nice thing about this is it's very fast. It's 100,000 times faster than hydrodynamic simulation. So we can, it's very efficient. So our goal is to present an improved emission line model with Galacticus and constrain luminosity functions for emission line galaxies with existing observations. So here we are presenting a model for star-forming regions of H2 regions using Galacticus. And in the future, we hope to incorporate H2 regions ionized by AGN and also do predictions for Roman. And this is a quick recap of what we have so far. These are luminosity functions for 10,000 merger trees with Galacticus, and you can see 3 emission lines here, H alpha, nitrogen and oxygen lines. And with high mass merger trees, you can populate more luminous galaxies, and of course you need a larger sample of merger trees to populate the luminosity functions. And this is without any calibration. So without any recalibration, we can also produce the observed star formation rate functions distributions matching observations of Robotham et al. 2011 from Gamma survey. So this is very promising, and stay tuned for this work. And come by my poster, and I'm happy to talk more. Thank you.
All right, as we're pulling this up, my name is Tim Carlton. I'm a research scientist at Arizona State University, and I wanted to talk to you about lessons we can learn from Hubble and what we can apply for learning with Roman. In particular, I'm talking on behalf of this large HST archival program, SkySurf, which is analyzing the whole HST extragalactic archive to try and understand both the galaxy light that we see in HST as well as the diffuse backgrounds that we see. And the first of 2 messages I want to really send to you today is that if you're interested in thinking about what you're going to see with Roman, a great place to start is with Hubble. We have a very similar telescope and instruments that you can start looking at. And if you consider the HST archive that we're analyzing, and we're going to publish catalogs for this whole survey. We've got 7 square degrees, we've got 40 million objects. It's not a huge survey with Roman, but it's a great start to start looking at some interesting objects. So for example, I'm interested in dwarf galaxies and diffuse galaxies, and so this is an image where the main target was some background quasar, and we just had this serendipitous discovery, identification of a more nearby galaxy that just happened to end up in the field. And if you want to think about what are we going to see with Roman, this HST archive is a great place to start. The other message I want to convey to you is that the backgrounds themselves are really astrophysically interesting. In SkySurf, we've identified this diffuse background that is present in HST with C3IR imaging. This can provide constraints on the diffuse extragalactic background light, but then also the backgrounds that we're seeing can be used to study the zodiacal light and diffuse galactic light that are in front of that extragalactic signal. And this is just something we've started to do with all of our HST archive, and given the wide area of Roman, this is something that we can really improve on, and definitely should be done to study these backgrounds. So thank you.